In this part, we'll be looking at twinning. Twinning as a plastic deformation mechanism. We have looked at slip as one of the important plastic deformation mechanisms, and we have seen slip occurs on certain crystallographic plane along some crystallographic directions. We'll be looking at twinning in such scenarios of, let's say, twin direction and twin plane. We know that these are two important deformation mechanisms where the plastic strain can be accommodated by material when they are deforming. So let's revise what is slip first and then try to understand twinning in terms of slip. So we have a crystal which is shown over here, and let's say we apply some shear stresses on it, and let's consider the slip first, the case of slip first, and you know that it occurs on certain slip plane and slip direction. And let's say this crystal gets sheared, and you know that when it shears it forms a step on the surface and it retains the crystal structure too. Now what happens during twinning? Let's look at this scenario. So when you apply a plastic strain or when you try to deform a material, the plastic strain will be accommodated in a way where twinning occurs and it also retains the crystal structure, but in a different way. Let's look at how twinning occurs. So we have a twin direction which is mentioned or shown over here, and you have a twin plane. And when I apply a plastic strain, this is where the twinning is occurring, and there is a shape change which is associated with the twinning. But if you look at this carefully, what has happened here, that shearing occurs along this twin direction and it has occurred on some particular plane which we call it as a twin plane. Also, if you look at this boundary is called as a twin boundary too. Now if you look at these two parts of the crystal, you can see that there is a crystal structure retention, but there is a change in the orientation. You can see here that there is a change in the orientation, and you can find that across these boundaries there is one-to-one correspondence of this point. So this point is a mirror image of this point, and this sometimes this plane is also called as a mirror plane. So this is a twin plane which is also called as a mirror plane. Let me write that down. So this is also called as a mirror plane. And you can see that there is a change in the orientation, while in case of slip there is no change in the orientation. So you have this as a parent crystal and this as a twin crystal which is oriented or mirrorly oriented with respect to a parent crystal. Now let's look at twinning in more detail. So we have a shape change, and that is associated without change in any crystal structure. So let's say you have this parent crystal and this parent crystal, and in between when you apply a shear stress, the twinning will occur along certain direction. We have seen that as a twin direction, and we have considered that plane where on which the twinning starts. We call it as a twin plane, or the twin plane is a plane between parent and a twinned region. And you have seen that this twinning occurs with no diffusion. So the atoms moved or sheared in such a way that there is no long diffusion occurring in the material, and generally it occurs at low temperatures. However, there is a movement of all atoms, and this movement of atoms occurs in a very disciplined way. We'll be looking at these aspects of twinning as we move along. And this movement of atoms which occurs in a disciplined way, and it occurs in the same direction and at the same time. So this same direction is nothing but our twin direction, and this disciplined way occurs at the same time, at the same moment, and that is how the change in orientation occurs because of this disciplined movement of atoms along the same direction and along the same time. So we have seen that slip versus twinning. You can say that there is a slip which is occurring here, and there is a change in the shape, or the plastic deformation or the plastic strain is accommodated using a slip mechanism. While in case of twinning, you can see that there is a change in orientation, and this happens, the twinning happens along a particular direction, and there is a shape change which is associated. So you have two different mechanisms where the plastic strain can be accommodated. One is slip and one is twinning. In this case, there is no change in orientation. In this case, there is a change in orientation. We'll be looking at when slip and twinning occurs. We'll see what are the external parameters by which slip and twinning gets affected. And the competition between slip and twinning also we'll be looking at. So let's look at twinning mechanism, and let's consider the face-centered cubic. If you open any standard textbook, they will be explaining twinning in terms of abscessive materials. And you know, in abscessive materials you have ABC stacking. So we have seen this stacking when there is ideal stacking which is occurring in case of abscessive. So here I have mentioned three layers, ABC, and A is represented by green, B is represented by red, and C is represented by this ash color. And this is a 2D picture where you have this direction to be bar 2 1 1, and this direction is 1 1 1. So what will be these planes? So all these planes will be, so if this is my 1 1 1 direction, so these planes, all these horizontal planes will be 1 1 1 planes. So these planes, these are all 1 1 planes. This is a stacking of ABC which are 1 1 1 planes, and you have this direction, that is bar 2 1 1, and this you can see here, that is a Burgess vector which is A by 6 bar 2 1 1, which is nothing but a Shockley partial. And we have seen that this Shockley partial which causes a stacking fault in a material. We have already discussed this when we are discussing about a stacking fault in abscessive materials. So we have this Shockley partial. So when I move one layer, let's say if I move B layer over A layer by A by 6 bar 2 1 1, I create a stacking fault. That is what we have seen. Now let's look at how twinning occurs. So for that, let's mark two planes. Let's mark these two planes here. And now let's mark these three planes, or these three lines which are indicating if this is a bar 2 1 1 direction, so these planes will be bar 2 1 1 planes, and this direction, when atoms moves in this direction, it creates a stacking fault. Now in twinning, what happens? We have a coordinated movement of atoms over each other. Now how that coordinated movement happens, we'll be looking at it. And it happens in a very disciplined way. We have seen this in our previous slide, that there is a coordinated movement of atoms in a disciplined way along a particular direction, and that's how twinning occurs in a material. So let's put your attention in this and try to understand how twinning occurs in abscessive material. So we have this ABC stacking, and we'll be displacing now these atoms or layer of atoms by A by 6 bar 2 1 1 in a very disciplined way. Let's do that. So you have all these three layers which have glided on this plane. On this red plane, all this top layer has glided by A by 6 bar 2 1 1. And now you can see that this layer is falling over this layer. let me change this layer to A layer. So this becomes an A layer. This becomes an A layer. Similarly, this becomes B layer and this becomes a C layer. Now this one layer has moved over this layer. Now what we do a coordinated movement is that this layer, that these top two layers will move by again A by 6 bar 2 1 1. Now let's move these two layers. So when it moves, you can see that this is now falling over this layer and this is falling over this layer. So we can change their color and now this becomes a C layer and this becomes a layer. Now let's move this top layer by again A by 6 bar 2 1 1. And now you can see that it has moved and this layer is now falling over this layer. So that is nothing but our B layer. So let's change its color. And now if you look at this region between these two boundaries or these two planes which we have moved it, we can see that there is a formation of twin. Let me mark that over here. You can see that there is a formation of twin. Let's consider this direction, and this direction. You can see that there is a twin which has formed across this boundary. Let's consider this plane and let's consider this boundary, these atoms over here. So it is exactly a mirror image of this. You can see here. Similarly, if you consider this boundary, this point is exactly a mirror image. So these planes are twin planes. Let us mark that also. So these planes will be twin planes. These two planes. And this direction was twin direction, which is nothing but a direction given by magnitude of this Shockley partition. And that is how twinning occurs. So let's understand or let's revise what we have done here. So let me write it down. So we had this ABC stacking. We have this ABC stacking. What we have done here, we have considered, let me mark those planes and let's consider these planes which are in between. Let's consider these planes which are in between, and what we have done, we have moved in first attempt. In first attempt, what we have done is that we have moved everything by A by 6 bar 2 1 1. Along this direction we have moved. In next time, what we have done is that we have moved B and C layer by A by 6 bar 2 1 1. And in third time, what we have done that we moved only C layer by A by 6 bar 2 1 1. So what we have actually done that we moved A layer by A by 6 bar 2 1 1 and B layer by 2 times of bar 2 1 1, A by 6 bar 2 1 1, and third layer, that is a C layer, which we moved by 3 times of A by 6 bar 2 1 1, and which resulted in the twinning of this region or formation of this twin. So these are a deformation twin which forms during the displacements of these atomic layers above each other in a coordinated way. You can see that A has moved just by 1 unit, B has moved by 2 units, and C is moved by 3 units. So that is a coordinated movement has happened, and that resulted in twinning of a material. If just only one layer moves, we create a stacking fault. But if that stacking fault which is being formed, if it happens in a coordinated way, we get a twinning in a material. Now let's move ahead. And this is what I was talking. Let's say we have a layer you have B layer and you have C layer, and it shears in a such a way that A layer displaces by 1 unit of B, B layer displaces by 2 units of B, where B is a Burgess vector, or that Burgess vector is nothing but a Shockley partial here. So we have 2 times of that Shockley partial, that is nothing but A by 6 211 type, and this C layer moves by 3 times of that Shockley partial, and thus we create a twin. And what will be the interplanar distance between these 3 layers? That is D111, and it can be given as A upon under root of S square K square plus L square, which will be A upon root 3, because all these ABC planes are nothing but 111 type of planes. Let me write that down also here. So all these planes are 111 type of planes. And now let's see what will be the Burgess vector. We have seen this. So we have a position B, or when a B layer moves, it moves in this way. So if it doesn't move in this way directly, so it moves along this way, which is A by 6 bar 211, and this is nothing but our Shockley partial. So what will be the strain which is being developed, or strain which is being accommodated, I will say, when twinning occurs in a material? So you can see that this tan theta you can get as 3b upon 3d. So we find shear strain in a such a way that the tan theta can be written as 3b upon 3d. So you have 3b, which is nothing but this Burgess vector, which is nothing but a Shockley partial here. So it has A by 6 bar 211. So we have to find out magnitude of this Shockley partial. And you have this D, which is nothing but an interplanar distance, and it is given by A upon under root of S square plus K square plus L square. Now HKL is 111. So you have D to be coming out to be A by root 3. So this magnitude of this vector is given by A by root 6, and magnitude of this D is given by A by root 3. And the shear strain what we get is 1 upon root 2, which comes out to be 0.7071. And this strain is a massive strain. What I am saying that the amount which the strain being accommodated by a material is massive. So this is a massive strain. What do I mean by? Let me explain it to you by taking an example of elastic deformation. Let's say you have a yield strength of a material to be 200 MPa and Young's modulus to be 200 GPa. Let's say this is for a steel, and what you get a strain, which is the strain which is developed in a materials will be 0.001, and this strain, if you compare with this strain, this is much smaller strain. You can see the magnitude or the strain which is formed during twinning, or strain which is being accommodated by a material during twinning, is massive. And that is why sometimes this twinning is called as a massive transformation or a military transformation. Why military transformation? Because the A layer is moved by 1 unit of B, B layer is moved by 2 units of B, and C layer is moved by 3 units of B. And let me tell you once again that this is a coordinated movement. This movement is happening simultaneously. I have shown you after one after another, but this movement happens simultaneously at the same time along the same direction. So this is a coordinated movement of these atomic layers, and thus it results in twinning. And such mechanisms, if you find in a book, they consider them as a massive transformation, because the shear strain which is being accommodated during this plastic deformation is huge amount, that is 0.7071, and the coordinated movement of atoms along a particular direction at the same time. That is why this transformation is considered as a military transformation. Now let's move ahead. Now let's understand twinning mechanism in case of BCC. We have seen this stacking of planes in case of BCC, and we have the stacking of 112 type of planes. Let me mention over here. So these are all 1, 1, 2 type of planes, and these are all 1, 1, 2 type of planes, and we have seen the stacking of these 1, 1, 2 type of planes as A, B, C, D, E, F, again A, B, C here. Now let's consider this plane, and we move by A by 6 bar 1, 1 direction, and let's move this, let's mark these planes first here and see how the twinning mechanism is different in case of BCC as compared to FCC. Now let's move these atoms. Let me move these atoms over here. Now if you see that there is these atoms are falling over each other, and thus this, what you say, this fault in a material or a stacking fault in a material will not be stable, and thus you can see that twinning in this direction becomes difficult. So when I moved twinning, or when I moved these atomic layers in this direction, there is a creation of high energy configuration, and that is not favorable, and thus this will not lead to any twinning. Now let us do one thing. We move these atoms in another layer by 2 units, and let's do that. So originally the atom was here and I moved in this direction. Now you can see that this configuration is energetically favorable, and thus you can form twins in such directions. Now we have moved this A layer over this layer by A by 6 bar 1, 1 magnitude. Now what we can do when you want to form a twin, we can move this B layer and C layer by again one more unit, that is A by 6 bar 1, 1 type, and last step will be you move C layer by another unit which forms A by 6 bar 1, 1 type, and thus we can get twinning. So here you can see clearly, let me mark that here. So if I try to make this or try to connect this, so we have moved this A layer by 1 unit of A by 6 bar 1, 1. Now if I move this another layer here, so that will be A by 6 bar 1, 1. Also same, I have to move it here by A by 6 bar 1, 1. And again the last step will be, again I have to move this C layer, which when this atom reaches here, I can move it another A by 6 bar 1, 1. So what we do is that when we see, let's say A, B, C, D, E, F, what we do is that, and here let's say A, B, C, and we marked F as a twin plane. So we moved this by 1B, this we are moving it by 2B, and this we are moving it by 3B. And thus we can form twinning in case of BCC. And this twinning is can occur only on 1, 1, 2 type of planes. So this is a twin plane, this is a twin plane, and this is a twin direction. So yes, we get twinning in case of BCC also. So when we moved these atoms, or this layer of atoms, we have seen that this configuration was not energetically favorable. So we call that as an untwinning process. Rather, this position, so let me mark it over here. So we have initially this A layer over here, and when we moved in this direction, this is an untwinning process. While if we move in this direction, this is a twinning process. So you have untwinning process over here happening, and you have twinning occurring here. Okay, so in case of BCC, you have twinning and untwinning occurring based on the gliding direction. So that is different scenario in case of BCC. So in the case of FCC, even if you move either direction, you get twinning. But in case of BCC, it's not so. You have twinning sense and untwinning sense. And that is what I have written over here. So you have a twinning and untwinning sense, which comes along the direction. So this is a twinning sense, in this direction, and this is an untwinning sense or anti-twinning sense. And that is how the twinning mechanism in BCC depends on the direction of shear stress. So if you apply shear stress, or if the atoms are gliding in this direction, this will not cause any twinning. But if you do it in this direction, it will cause twinning. And thus, some of the deformation mechanisms, or in case of BCC, like twinning, they are directly dependent. And thus we will not see isotropic behavior when there is a twinning occurring in case of BCC materials. Now let's move further and see what is a shear strain. We have calculated a shear strain developed in case of abscessive material. Here we try to find out a shear strain developed in case of BCC. So how do you find out that shear strain? So you consider the glide magnitude, which is A by 6 111 type, and you consider the distance between these two planes. These are 112 type of planes. So the distance between these two type of planes will be given at D112, and that you can find it out by A upon under root of S square plus K square plus L square. And if you find out a shear strain magnitude, which comes out to be 0.707, and that is also a huge strain which is being accommodated during twinning of BCC materials. So we have seen that the shear strain which can be accommodated, whether it's a abscessive material or BCC material, when plastic deformation is occurring because of twinning mechanism, you can see that the shear strain is almost very high, which is 0.707, and which is much higher than the elastic strain develops in a material. Now let's move further. And now talking about twinning, so we distinguish twinning when we have twinning forming during a mechanical deformation, or when you deform a material you get a twin, and that twin is called as a mechanical twin. While there is another twin which you can see in the microstructure, that is called as an annealing twin. So here you can distinguish mechanical twin versus annealing twin from the microstructure. So mechanical twin will have this lens kind of shape. So it has a lens shape. You can see that there is a lens shape, while annealing twins will not have this kind of lens shape. So when you have a lens shape, you can say that this is a mechanical twin, or this twin has formed during deformation of material. While these twins, where they have perfect interfaces, those are annealing twins, and these twins form during heating or annealing of the material. And why this lens shape? Now you can see here that we have seen the coordinated movement of atomic layers, and that is by a magnitude of Shockley partials. So when we are deforming materials, we get mechanical twin, and you can see that this Shockley partials which are mentioned here, so you have these coordinated moments, and thus you get a lens shape here. While in annealing twins, that is just another orientation, just an orientation change. It doesn't form because of the movement of atomic layers above each other. This is just formed because of the interface attains a lower energy while annealing, and this can be considered as just an orientation change, and that is why they have lower interfacial energy as compared to mechanical twins. So mechanical twins will be associated with an elastic strain energy, while these twins doesn't have that high strain energy associated with it. Now let's look at this annealing twin and mechanical twin again, and you have this alloy which shows this mechanical twin. So you can clearly see that these have a lens shape, while these are annealing twins, and you can see that there is just an orientation change. So this grain is which I called as a parent grain, and this is a twin part. Let me write that down here. So we have this as a parent, and this is a twin part, and you can see that there is just a orientation change with parent and twin part. And the question here is why we get this kind of shape. So we have seen the coordinated movement of atoms, atomic layers, and that creates or that accommodates a shear strain. So you can see that when a layer moves, let me mark it over here. Let's say you have A, B, and C layer which moves in this way, and so you have this 3B, you have 2B, and here let's say B, and this is our mirror plane or a twin plane. So you can see that you have coordinated movements, and thus when there is a shape formation of this twin, you will have the displacement is decreasing and it comes to 0. That is why you get kind of a lens shape to have minimum strain energy. So you'll have minimum strain energy at this location where the displacements are 0. That is why we get this lens shape. Now let's look at annealing twin. So you have this annealing twin which has a twin plane, and across this twin boundary you have this perfect coherency. Let me draw a schematic for you. So you have this, let's say you have this parent material and there is a twinning occurring in this material, and you can see that the twinning has perfect coherency. So we'll have the perfect coherency at these mirror planes or these twin planes. And here just the stacking sequence has changed. It is just an orientation change, and these interfaces will have low energy because there is no strain energy associated with these annealing twins. So these are also called as growth twins, which doesn't have any strain energy associated with. So you can consider just an orientation change here. And here we form this mechanical twin by coordinated displacement of atoms along a particular direction at the same time. And thus this is associated with the strain energy because this forms during the plastic deformation of a material. Now let's move ahead. Let's look at deformation twinning in more detail. So we have this deformation twin. Let's plot a stress required for twinning with respect to temperature. So we have this stress required for twinning can be given as K gamma SF upon GPS. So you can say that if the gamma SF, that is a stacking fault energy of material, is high, the stress required for twinning will be higher. So thus, let me write it down here. So if I have gamma SF to be higher, tau T, that is a stress required for twinning, will be higher, and thus twinning will be shown for materials for which the stacking fault energy is lower. So you can see twinning occurring in a material where their stacking fault energy is much smaller, something like at the order of, let me mark that also, let me write that energy value is also something like 20 less than 20 millijoules per meter square. So this is a typical values where you can see twinning occurring. You can see twinning occurring at higher values of gamma SF also, and we'll be looking at such cases. So let's consider this case, and here we are plotting a twinning stress or a stress required for twinning with respect to temperature, and here there is no temperature term. So what we can consider that the twinning stress remains more or less constant. So you have twinning stress, and this K is a proportionality constant where G is a shear modulus and B is a Shockley partial here. Let's consider a case of abscessive material. So here B will be the Shockley partial. And we have seen the variation of tau CRSS with temperature, that is for slip to occur. And now we'll be looking at this deformation twinning and a slip mechanism, how competition between them occurs with respect to temperature and with respect to strain rate too. And for slip, you can see, as we have seen, that there is a decrease or a stress required for slip, which decreases with increase in temperature. And here from this diagram or this schematic, you can see that at temperatures above certain temperature, let me mark that here also, let me mark that here. So you have this temperature above which slip occurs, because slip stress is smaller than twinning stress, and below which twinning can occur. So you can see above this temperature the slip stress is smaller than the twinning stress, and thus the slip will occur here. Below this temperature, twinning stress is smaller, or the stress required for twinning will be smaller, thus twinning will be preferred over slip. So below this temperature will not have slip, the material will deform by twinning. Now this happens, or slip happens, at let's say particular strain rate, and let's say this strain rate as epsilon 1 dot, and you know that the slip stress increases with increase in the strain rate. So here epsilon 2 dot is higher than the epsilon 1 dot, which is a strain rate. So this strain rate is higher than this strain rate. So we have seen that the dislocations cannot move readily, and thus what happens, the slip stress increases. And you can say that if you consider this scenario where at strain rate 2, let me mark that also. So if you consider this scenario, so you can say that here slip will occur, and below this temperature twinning will occur. And let me mark these temperatures as T2 and T1. So you can clearly see that T2 will be greater than T1, and here epsilon 2 is greater than epsilon 1, and thus you can say that if I increase temperature, slip will dominate, but if I increase strain rate, the twinning can occur at higher temperatures too. So when there is a high strain rate deformation, you can see that twinning can occur at higher temperatures. So we have epsilon 2, this strain rate is higher than this strain rate 1, and you can see that twinning here in this case was occurring below T1 temperature, but in this case the twinning can occur at T2 temperature, which is higher than this T1 temperature, and thus twinning can depend on the rate of deformation. So if the rate of deformation is much higher, twinning can occur at higher temperatures too. So these are certain materials which I have marked here, stacking fault energy corresponding to them, and you can see that aluminum has high stacking fault energy. So if you look at the deformation or deformed microstructure of aluminum, you will not observe any twins in it. You will see that aluminum will rarely show twinning, while when you deform silver or gold, which has lower stacking fault energy, when they deform by twinning. However, if I want to observe twinning in case of aluminum, I have to deform this aluminum at very high strain rate, or maybe a shock deformation, the strain rates of order of much higher than what we see the strain rate or deformation rate at room temperature, let's say 10 to the power minus 4 per second. We'll be looking at it shortly. So we can say that silver can show twinning for the same deformation condition as compared to aluminum, because aluminum has high stacking fault energy. So as I decrease the stacking fault energy of a material, the twinning tendency increases. Let us write that down also. So if I decrease stacking fault energy, twinning increases. Now let's move ahead and see some of the parameters which affects twinning. So the first parameter is stacking fault energy. We have seen if you have high stacking fault energy, twinning tendency goes down. If you have higher strain rate, here in this case we have seen if you have high strain rates, the twinning will be preferred. So if you have very high strain rates, twinning will be preferred over sleep. If I increase the temperature, if I am increasing the temperature, the sleep stress is decreasing. Thus, when I increase the temperature, the twinning tendency goes down. And we'll be looking at what is an effect of grain size as we move along. So grain size also affects twinning. So let's consider twinning plane and twinning direction. So we have this twinning plane for HCP structure, 10 bar 1 2 plane and 10 bar 1 direction. You have BCC, we have seen this 112 plane as a twin plane and 111 as a twin direction. In case of FCC, we have 111 twin plane and 112 twin direction. And these are the certain examples of these classes of crystal structure which shows twinning. And if we compare twinning and sleep, so you can find that if I compare twinning in case of BCC, you can say that the twin plane is exactly equivalent to the sleep plane and twin direction is exactly equivalent to the sleep direction. Similarly, in case of FCC material, you have twinning occurring on 111 plane and sleep also occurs on 111 plane. Here in this case, the twin direction is 112 direction, but the sleep direction here is 110. However, this can be splitted into two partials which are of 112 type. And in case of HCP, you have twinning to be occurred on 10 bar 1 2 plane and 10 bar 1 direction, and this depends upon C by A ratio. Let me write that down also. So we have twinning depends on C by A ratio. So you can read about what is a C by A ratio in case of HCP materials, and depending on the C by A ratio, we have seen a variation in twinning, or twinning plane can change and twinning direction also can change. And now let's move ahead. So now let's consider that when twinning will occur and when sleeping will occur. So this statement which I would like to mention, when sleep becomes difficult, twinning pitches in. So when sleep is difficult, you have twinning mechanism which comes in. So you have to find out what are the conditions for which sleep becomes difficult. So first condition is low temperature. At low temperatures or sub-zero temperatures, let's say at liquid nitrogen temperatures, the mobility of dislocation decreases and thus the material cannot deform by sleep mechanism. So that's why the twinning can take place in a material which accommodates a plastic strain. The next is high strain rates. So when I talk about high strain rates, so those are of the order of 10 to the power 2 to 10 to the power 4 per second. At these high strain rates, material will be subjected to very high or sudden deformation, and that sudden deformation can be accommodated using twinning rather than sleep. So material favors for twinning at high strain rates. Also, we can consider that at shock deformation, which is of the order of the strain rates are of the order of 10 to the power 9 to 10 to the power 12 per second, at these conditions, the material will deform by twinning rather than sleep. So the next mechanism or the next condition will be slip systems. So when you have lower active slip systems, let's say in case of HCP material which have only 3 slip systems. Let me write it here. In case of HCP, you have 3 slip systems. We have already discussed this. So in such cases, in such crystals, you will find that twinning will take place rather than sleep. And the next parameter is the composition. So if you have a lower stacking fault energy, that depends on the composition of a material. So if you decrease the lower stacking fault energy, or if you decrease the stacking fault energy, you will find that twinning will take place. And grain size. So if we look at the tendency of twinning with respect to grain size, what we find that the twinning can occur for a certain grain size range. So you can see that the tendency for twinning to form in a material will be for certain grain sizes. Let's say at higher grain sizes also you will have de-twinning here, we have mentioned here, but at higher grain sizes you will have slip to occur, whereas at lower grain sizes, if twinning starts form, it is accommodated by a process of de-twinning. So here the plastic deformation will occur by twinning, de-twinning of a material. Rather at higher grain sizes you just have a slip which is occurring. So you have a twinning tendency for a certain grain sizes. Now let's understand some of the important points about twin. So twin nucleation is difficult, but propagation is fast. What do I mean by that? Let me write it down here. So when we talked about these three stackings A, B, C, so A, this moves by 1 unit of B, that is somewhat difficult. This initiation is somewhat difficult, but once this has been initiated, what happens is that this movement of B by 2B and C by 3B occurs immediately. So only nucleation of this A to another layer by moved by one unit of B, that is a Shockley partial, to create a stacking fault here, that is only a bottleneck here. But once it starts, then twin propagates faster. And how much fast it is? So twin propagates with a velocity of sound. And what's the velocity of sound in a material? Let's say in steel, it reaches to 5000 meters per second. And here I would like you to look at tin cry. So there is a one good video available on YouTube. So visit this, what is tin cry, and look at some of the work of Professor HKDS Padesha, who is from University of Cambridge, and he has extensively worked on twinning. And let's look at this video on YouTube. So for a curiosity, try to see what does exactly tin cry means and how twinning is related to it. So with this, we have understood that twinning is one of the plastic deformation mechanism, one of the important plastic deformation mechanism, which comes when slip becomes difficult. And we have seen when slip becomes difficult, we have looked at all these parameters. And when these parameters makes slip difficult in a material, you have plastic strain to be accommodated by twinning mechanism. And with this note, I will stop here.